Okay, so in this bit, we'll just prove a few theorems about series of functions. The first two are kind of like really like kind of trivial, I guess. And then the third one is going to be the Weierstrass M-test. So I decided to do all of them in this video just because the first two are really like 1-2 line proofs. So the first theorem here, so is just like, these are just sort of like basic sanity checks that our definitions actually do what we want. So a series GK of functions on a set S so consider a series, right? Consider a series of functions like this. So let's say from k equals 0 to infinity. If each gk is continuous and the series converges uniformly on S, i.e. the partial sums converge uniformly on S, then the function f of x which is represented by this series is continuous on S, right? So if we're assuming the series converges uniformly on S, then f is automatically defined on all of S, but it also turns out to be continuous. The proof is extremely simple. Since each gk is continuous, then each fn, which is the sum from k equals 0 to n of gk, gk is also continuous on S. This is all on S. Then since fn converges to f uniformly on S, f is continuous. So the only step here that isn't like literally trivial from the definitions is just the fact that since each gk is continuous, then the partial sums are all continuous, right? But I mean, for us, that's trivial because we already proved a theorem that says that the sum of two continuous functions is continuous, right? So any finite sum of continuous functions is automatically continuous. You know, that is something we're implicitly using like a proof we already did in the past for that, right? So it's not just like automatic from the definitions, but yeah, that's kind of the real material. That's the substance of this entire statement here, is that like you can infer from the continuity of the terms here that the overall function itself is actually continuous, provided that the series converges uniformly, of course, right? So the uniformity of the convergence is like absolutely critical. All right. The next one is just, so if a series sum from k equals 0 to infinity of gk, oh, right, sorry. Well, I guess I should probably introduce this a little bit. Right, so as you saw in the the first example in the previous video, right? As we saw, so for a sequence, or for a series, sorry, of functions, gk from k equals 0 to infinity of x, right? well, really just the sum of gk is the better notation, but just remember that these are actually functions, right? Then say the partial sums are fn, which is the sum from k equals 0 to n of gk. Then fn as a sequence is a uniformly Cauchy sequence on S if and only if, right, for all epsilon greater than 0, there exists an n such that for all n m greater than n, we have and you know, and for all x in S, we have the absolute value of fn of x minus fm of x is less than epsilon. In this case, this is the same as requiring that for all epsilon greater than 0, there exists a capital N such that for all n and m greater than capital N, for all x in S, we have the absolute value of the sum from k equals m. Oh, and let's say, and well, we can assume that n is greater than m. K equals m to n of gk of x is less than epsilon, right? So this, if you remember the Cauchy criterion for series of numbers, this is the exact analog of that just for functions, okay? So this would be called the uniformly Cauchy criterion, the uniform Cauchy criterion. So the uniform Cauchy criterion for series of functions. Right. So we had a Cauchy criterion for series, which was just like you'd sum k from k equals m to n of terms ak, right? But now instead of just terms which are just numbers, the terms are functions. And we just require this to be true for all x in S at the same time, right? To make it uniform. So that's the uniformly Cauchy criterion for series. That was exactly what we used to show that, that the sequence of partial sums of the first example formed a uniformly Cauchy sequence previously. I just didn't give it a name back then, right? But I mean, it's just immediate from this because literally fn minus fm equals the sum from k equals m to n of gk, right? So it's literally all I'm doing is just substituting in our expression for fn, into this fn minus fm and turning it into the gk's, okay? So that's the uniformly Cauchy criterion for series. So, so then we can say this is the theorem, let's see, 25.6. If series gk from k equals 0 to infinity satisfies the uniformly Cauchy criterion on, or the uniform Cauchy criterion on S, then the series converges uniformly on S, right? And this is like trivial. Set fn to be the nth partial sum. Then by assumption, fn, the sequence fn, is uniformly Cauchy. So fn, this is on S. So fn converges uniformly on S. There you go. Right. This is all just, it's all pretty much just terminology, honestly. It's not, there's no real content right now here. Okay? Okay, so now let's do something a little bit more interesting, right? So I want you to actually remember, you know, so like recall for, you know, the sum x to the k on 1 plus x to the k, 1 x to the k over 1 plus x to the k, right? We, you know, on 0a, we showed this was uniformly Cauchy by bounding like the sum from k equals m to n of x to the k over 1 plus x to the k by you know, the sum of a to the k from k equals m to n, which then we said is, you know, less than a to the m times the sum from basically k equals 0 to infinity of a to the k, right? Which is a to the m 1 over 1 minus a, right? So, but like, well, yeah. But so I think what I want you to notice here is that this is a convergent series, and the terms are upper bounds on the absolute value of gk of x, okay? So basically it's like, if you can get a handle on how big gk of x can get, and you get these like upper bounds, you get an upper bound on each gk of x, and then those upper bounds form a convergent sequence, you can basically repeat this exact process for like any situation where that happens, and you'll be able to show that the series is uniformly Cauchy that way. And that's basically what the Weierstrass M-test does, is just does that like in general, okay? Like this is also how you'd show that the sum of like 3/4 to the n gn of x converges uniformly in the second example, right? From the previous video, because it's this, you know, this 3/4 to the n, right? The absolute value of 3/4 to the n gn of x is less than or equal to just 3/4 to the n, right? And if you sum up 3/4 to the n, you get a convergent geometric series, and it's the exact same thing. And of course, it's not, obviously it's not always going to be a geometric series. That's just a coincidence here. But the point is, you get a convergent series. You get a convergent series of these upper bounds on like the absolute value of each term, basically, right? So, okay, let me state the Weierstrass M-test. So I'm going to phrase it a little bit differently from how they do, because it's kind of awkward the way they word it. So let GK be a series of functions defined on S, and suppose MK is a number for each k such that absolute value of gk of x is less than or equal to mk. Okay? And suppose further that the series of mk converges, you know, to a finite number, of course, which is I mean, that's the only way it can converge is if it's converging to a finite number. I just want to emphasize, right, that if it's converging, then it is converging to a finite number, right? So just to remind you that infinity, we don't consider it to converge to infinity. Then it's automatic from this that the series GK converges uniformly on S, okay? So let's see why. So let's show that the series of GK is uniformly Cauchy on S, okay? So let epsilon be greater than 0. The point is, like the ultimate like inequality, so important step. The absolute value, ultimately, like we're going to be trying to do that. We're going to try to bound this above, right, by something, and then get that to be less than epsilon. The thing we're going to bound it above by is first we're going to use the triangle inequality, which we love, right? And then this is going to be less than or equal to sum from k equals m to n of mk. And then since the series from k equals m to n of the series from k equals 0 to infinity of mk converges, we can make, if we call this star less than epsilon, right? Because if the series of mk converges, then it has to satisfy the Cauchy criterion for series, right? So that's what we're going to do. So let epsilon be greater than 0. Then since the series of mk converges from k equals 0 to infinity, it satisfies the Cauchy criterion for series, right? I.e., there exists a capital N such that for all n greater than m greater than capital N greater than or equal to m, sorry, we have that the absolute value of the series from k equals m to n of mk is less than epsilon. Since each mk is greater than or equal to 0, which of course is necessary in order for this to be true, right? If the absolute value of gk of x is less than or equal to mk for all x, then clearly mk has to be non-negative because the absolute value is always non-negative. So each mk is greater than or equal to 0. We can drop the absolute values. So k equals m to n of mk less than epsilon. Okay. Then for any n greater than or equal to m greater than this capital N, we have, by the logic on the next slide, that the absolute value of the sum from k equals m to n of gk of x is less than epsilon for all x in S. So sum of gk of x is uniformly Cauchy on S, which is what we wanted to show, right? We're showing that it's uniformly Cauchy on S. That means that the partial sums form a uniformly Cauchy sequence on S, which means that they converge uniformly on S, which is what we were trying to show, right? So, and remember, so the logic on the next slide here was this whole thing of like, okay, apply the triangle inequality, then apply the upper bounds, then we know that this is small because of how we chose capital N, right, for this epsilon. So there you go. That's the Weierstrass M-test. In the next video, which I think should be the last for this lecture, I'll show you a couple more examples of applying the Weierstrass M-test to conclude that a series is uniformly convergent.